Hello everyone, my name is Vladimir Kurechik Jr. I'm a PhD student of Southern Federal University in Russia. Computer-aided design department deals with the development new methods of electronic computing equipment design. So I would like you to present some investigation in this field. One of the most labor-intensive stage of the electronic computing equipment engineering is the stage of construction engineering. Among the common tasks of constructive engineering, the placement problem is one of the most difficult. The current algorithms of automated engineering don't solve the task or need a lot of process time to search the effective solution. Thus, there is a necessity of development of new approaches, methods, and algorithms to solve the placement problem. So we developed a combined search with the use of the strategies of evolutionary modeling and the principles of decision making of the basis of natural mechanisms. In general terms, the placement problem can informally be presented in the following way. There is a set of elements connected to each other according to the principle and electric circuit of the object being created. It's necessary to place the elements within the communication area in such way that the defined net objective function has a local or optimal value. The main aim of the placement algorithm is to minimize the total length of this connection. At poster, there are presented the distance between the circuit elements and the whole length of all the connections. It's reasonable to point that during the elements placement, the minimization of the total length of conductors usually causes minimization of the number of in-circuit intersection and total length of the critical connection. One of the main ways of reduction of placement problem difficulty is a reduction of its dimension. The multi-level macro engineering is very effective in the case of the considered placement problem consisting in thousands of elements at the same time. The initial task of great dimension is divided into the set of the identical tasks, a smaller dimension hierarchically put in each other that can be solved by means of one of the basis optimization methods. In 1980, Benoit Mandelbrot pointed out fractal geometry of natural systems. The fractal objects are self-similar. Their type doesn't vary in the case of scale change of their activity. Here we are given an example of one of the possible solutions of the placement problem on the basis of fractal aggregation. It is based on the following principles: creation of clusters, factorization of clusters, aggregation created in the condition of random, direct or combined addition of the elements to the cluster. Moreover, the process of cluster creation is based on the minimal array in a graph or hypergraph. The main difficulty of placement problem solving is the curse of dimensioning, processing of great amount of information. To solve this problem, we offer the combined search. Its description you can see on the poster. The initial information and the model of communication circuit are carried in the first stage. Then, on the basis of scale compression of the graph model in horizontal direction is performed by the creation of the minimal clusters and fractal aggregation. At the second stage for search, the genetic algorithm is carried out, letting make effective change. At the third stage, unpacking of the graph model is implemented and the result is checked. In the case of unsatisfying result, the throwback to the first level is carried out in order to compress the circuit in vertical direction. Then the transition to the second and the third levels is completed to accomplish the algorithm of rearrangement and unpacking of the graph model. The use of such approach gives an opportunity to reduce the amount of computer resources, search time, and to receive optimal and quasi-optimal results in polynomial time. Here we show an example of combined search. A method based on the creation of minimal clusters and fractal aggregation. we have the communication circuit in the form of the graph G. Here objective function L of G consists in 105 conditional units. Let us present the fractal set. For example, we compress a graph in horizontal direction. For this purpose, we consider each line of the grid as one top of the new graph G1. We get an initial alternative solution ABC where objective function is equals 30. Then we make an arrangement of the graph tops according to the genetic algorithm. The results of genetic algorithm you can see at the poster. So we get a new alternative solution BAC. The objective function is equals 23. When we use the mechanism of fractal aggregation and graph unpacking after the transition from the fractal graph G1 to the graph G, we can find the graph G in a grid as shown on poster. 1 over the objective function is equals 95 conditional units. According to the search architecture, it is checked whether the stop criterion is reached. The stop criterion is achievement of quasi-optional value of objective function. If the value of the objective function is not reached, then we generate the fractal set. For example, the graph G, the graph is compressed in vertical direction. For that, each column of the grid is represented as one top of the new graph G. Then similar transformation are implemented for the graph G on the basis of the genetic algorithm. Then a result you can see on the poster. Then we unpack the graph, and as a result we receive the final placement with objective function is equals 78. As a result we receive a quasi-optimal solution placement as the value of objective function is reduced. That provides that the offered approach gives an opportunity to minimize the total length of connection. We develop the program product in order the determinant feature of the development algorithm, some research of time and solution quality for the various benchmarks were carried out. The examination of dependency of work time of algorithms on the amount of their elements. The results of our research are shown in poster. The results of the research make it possible to draw a conclusion that time complexity of developed approach is within the limits of polynomial dependence. Also, we consider dependency of objective on the number of elements. The analysis of undertaken research is shown that the quality of placement received by means of combined research on average at near 5% excels the result of placement received using the Knoven algorithm. So conclusion. The combined approach is offered in the work to solve the task of electronic computer equipment element placement. The new architecture of search based on multi-level approach is developed. The main difference of the offered approach is the division of search in two stages and usage of different methods on each stage. Such an approach gives an opportunity to parallelize the solution solving process. The genetic algorithm that allows us to get set of quasi-optimal solution in polynomial time is developed. The conducted set of experiments give an opportunity to define more exactly the theoretical estimates of temporal difficulty of placement algorithm and their way to work for the circuit of a different structure. Thank you for your attention.